All right, so right now I'm going to talk to you a little bit about horizontal asymptotes and how these things can be better understood using calculus. So, first things first, I'm going to refresh our pre-calculus knowledge of what horizontal asymptotes are. So check this out. If I am looking at a horizontal asymptote, remember that that's kind of a value, and technically it's a y value, that your function tends toward over time. So essentially, like, I might see a horizontal asymptote that looks something like this, and then maybe like this. We've also seen horizontal asymptotes with our parent function 1 over x, which, if you recall, looks something like this. It has a vertical asymptote too, but notice that it has these horizontal asymptotes, and this one's actually at x equals, or how about, sorry, y equals 0. It's a horizontal line. And so horizontal asymptotes are just kind of these values that your function tends towards as it continues out to negative infinity or as it continues out to positive infinity. Can you guys start feeling the limits happening already? All right. So let's talk about when we have different situations with horizontal asymptotes. Now, before we get into all of that, we do need to remember what the degree of a function is, because I'm going to throw that language at you and I want you to understand what I'm talking about. If I give you something like x cubed plus x minus 1, this is of course a polynomial, and the degree of the polynomial is 3 simply because the largest power is 3. So when I talk about the degree of a polynomial, I'm talking about the highest power that occurs in any of the terms of my polynomial. So, I mean, it could even be out of order. Like if I have something like this, the highest power here is a 5. And so actually that's the degree of my polynomial, even though all of these terms are kind of out of order. They're not in ascending or descending order. Okay, so now that we understand what degrees are, here's a couple of things to know about horizontal asymptotes. If you're given some kind of a function like this, and it's made up of polynomials, in general, we might describe polynomials in this way. So notice how I'm using the letters n and m to represent the highest power of either the numerator or the denominator. So the numerator itself, by itself, is a polynomial of degree n. So I'm assuming that's the highest power. The bottom, by itself, is a polynomial with the highest degree m. Overall, when you divide them, dividing polynomials does not create a polynomial, so this is actually a rational function. Now here's some things to know. All right, so here are the possibilities you can have with horizontal asymptotes based on the degree of either the top or the bottom. If the degree of the bottom, m, is larger than the degree of the top, then you have a horizontal asymptote at equals 0. And you can see that with our kind of basic parent function 1 over x, because technically x to the 0 power is just the number 1, and x to the first, yeah, if the top is smaller than the bottom, I get these asymptotes at x equals 0. All right, what happens if maybe the bottom degree is less than the top? What would that mean? Well, it actually means that there is no horizontal asymptote, so you don't have to worry about it. The last situation that could occur is if the degree of the top is equal to the degree of the bottom. So what would happen in that case? Well, it's kind of a cool situation where you wind up with a horizontal asymptote at x equals a over b. So the leading coefficients become the value of your horizontal asymptote. So it's a over b. And I'm going to kind of erase this stuff and get that out of the way. Okay, so for example, I'm going to go through these kind of quick. If I had x squared over an x cubed, the degree of the top is 2 and the bottom is 3, and 2 is less than 3, so that means I have a horizontal asymptote at x equals 0. Okay, if I gave you a different one that looked something like x plus 1 over, or how about x squared plus 1 over x minus 1? Notice how the degree of the top is bigger than the degree of the bottom. That would be this situation. So that means there's no horizontal asymptote at all. The last one would be if they were the same. So a situation where that might occur is like 2x squared plus x minus 1 all over 3x squared plus 2. The degree of the top and bottom are both 2, and so that means my horizontal asymptote is at the value 2/3, and on a graph that would be something like, right, 2/3, and my horizontal asymptote would happen right there. Okay, I know this has been a pretty in-depth review of horizontal asymptotes, but I always tend to forget those little facts. So I appreciate just taking the time and thinking about those again. All right, so I'm going to show you some of the most beautiful functions that I know of. I'm going to zoom in on these guys. So take a look at this first function. If you can't see it in the screen, I know the screen is kind of tiny, this is our first function. So notice how in the numerator the degree is equal to 1, the bottom the degree is equal to 2, and I can see when I zoom out that, yeah, the behavior as you go left to right on the infinity direction, this thing has horizontal asymptotes at 0. So that makes sense. Okay, how about this next one? I'm going to turn that one off and take a look at this one. Ah, it's so beautiful. It's got this excellent little dip in the middle, and then it seems to level off in either direction here. And if you look, actually, the degree of the top and bottom are equal. They match. And so that means that the numbers out in front, 10 over 3, that is going to be my horizontal asymptote. So if I type in y equals 10 over 3, there's that beautiful purple line that actually describes the horizontal asymptote for that function. Okay, the last one I'll show you looks like this. Another beautiful, excellent function. Here I see that the numerator has degree 3, the denominator has degree 2, and that means there is no horizontal asymptote. So if I zoom out, I mean, it's pretty obvious this thing is going off, like shooting off into infinity. It's not leveling out at all. It's not doing that at all. It's just going straight to infinity that way, or straight down to infinity that way. So there's no horizontal asymptote there. Okay, so what does this have to do with calculus? Well, I want to take a second and actually explore each one of those functions in terms of limits in calculus. Okay, so here's our first function that I want to try to inspect in terms of calculus. Now, I know that the degree of the top is smaller than the bottom, so I should have a horizontal asymptote at 0, but I want to confirm that. Okay, so think in terms of limits. I'm trying to find the limit of this function. Well, is x going to a single point? Like, is it only approaching the number 2? What's really happening here? When I look at horizontal asymptotes, I'm actually looking at the end behaviors of my function. How does it continue out this way? Does it go up forever to infinity, or does it kind of level out at a certain value? So I'm looking at the long-term behavior of this function, not as x approaches a single value, but as x approaches infinity. What is it doing? So this is a really new type of limit. Take a look. The limit as x approaches, and we're going to start with positive infinity. So as it moves into the positive infinity direction of this function, x plus 1 over x squared plus an x plus a 4. Now, like I always say, try to plug in values first. Try to do direct substitution first. And you might be wondering, how can I plug in infinity? Think in terms of a very, 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 very large number. So let's just think about this kind of conceptually. As a student, I prefer to think about 1 million. What would happen if I plugged in 1 million here, or like million down there? But again, you're thinking even bigger than that. Maybe you guys would like a Googleplex. So I'm thinking in terms of like infinity plus 1 over like infinity squared plus an infinity plus a 4. And again, I'm just plugging in infinity to represent a very big number. You cannot plug in infinity. And some people would probably hate me for even doing this. But I want to conceptualize a very, very large number. So the top, I mean, add 1 to infinity, you kind of just get infinity. Square infinity and keep adding it. I mean, you're getting really this infinity over infinity situation, which is an indeterminate form, friends. You can't evaluate this. It doesn't actually have any meaning. So I have to use a technique to evaluate this type of a limit. And we've already learned some techniques before when x was going to a single value. So now I'm going to teach you a technique for when x moves to infinity. I'm going to multiply by a very fancy 1. And the 1 that I choose to multiply by is going to be 1 over the highest degree in the overall rational function. So the highest degree here is an x squared. And so I'm going to multiply the top by 1 over x squared and the bottom by 1 over x squared. So I'm doing this to both. And essentially this whole number is equal to 1, so I'm not actually changing the problem at all. I'm just changing kind of the way it appears. All right, what happens? When I multiply this to each term, essentially it's the same as dividing. So I get something that appears like the limit as x approaches infinity of x divided by an x squared plus 1 divided by an x squared. So I've taken this and I multiplied it here. That's where I get the x on top and the x squared on bottom. Now I'm going to do it again here. I get essentially x squared over x squared plus x over x squared plus 4 over x squared. And now I'm going to take a couple of steps to simplify and cancel some things. Here, one of the x's cancels with one of those powers, so I have 1 over x plus, this guy doesn't simplify at all, 1 over x squared. Down here, both of those actually cancel, so I'm left with 1 plus 1 over x plus 4 over x squared. And now let's see what happens when I plug in infinity, or a very, very, very large number. So as x moves to infinity, as it grows larger and larger, what is now happening? Well, I'm going to pretend to plug in infinity again and just kind of think about this. Now pause for a second. I'm going to take 1 and divide it by a huge number like a Googleplex. What's going to happen here when I do that? If you're not quite sure, start thinking about numbers. 1 divided by 10. That's pretty small. 1 divided by 100, that's even smaller. 1 divided by 1,000, that's quite small as well. If I make that thing go off to infinity, like the bottom, if I divide by something huge, huge, this essentially becomes 0. So small that it's like arbitrarily small. Like insignificant is basically 0. And then same thing here. If I do 1 over infinity like squared, that definitely is just going to be like a 0. On the bottom I have this number 1. This thing is going to basically be 0. Same here. 4 over x squared. That's essentially 0. So what I have in the numerator is this winds up going to 0. And again, I'm thinking the limit. So what is kind of the numerator tending toward over time? Well, over time it tends towards 0, so the limit is 0. And then in the denominator, those are zeros plus a 1. which is 1. And hey, 0 divided by a number works. That's okay. This is essentially 0. All right, take a long walk back with me. When the numerator, the degree, is smaller than the denominator, the limit winds up being 0. So as you move from positive to negative infinity, your function tends towards 0. And that's exactly what we saw if we take a look at our functions again. That's exactly what we saw happen with our red line function here. By the way, if you're curious about negative infinity, think about substituting in just very large negative numbers now. And again, you're still going to see that this is going to 0, but sort of like in the negative direction. So it comes up from the negative y values. And you do see that on this graph. Notice that it starts kind of lower underneath the y-axis, and then it tends towards 0 after that. So kind of from the negative approach, it gets close to 0. Now that we know the technique, let's move through these other problems a little bit faster. All right, so our next function looks like this, where you can see that the degree of the numerator is 2, and that's the same for the denominator. So what I expect to have happen is that my horizontal asymptote will end up being the leading coefficients, 10 over 3. So let's apply limits as our function approaches infinity and see if this actually works. So if I take the limit as x approaches infinity of 10x squared plus 4x minus a 5 all over 3x squared plus 2x plus 1. Remember that my technique is to divide by the highest power in the whole rational function. So if I look at the top or the bottom, I'm looking at all the terms. What's the highest power that I encounter? And in this case, it's just 2. So I'm essentially going to multiply by 1 over an x squared all over 1 over an x squared. And that essentially winds up being the same as dividing by x squared. Every term gets divided by x squared. So I have 10x squared over an x squared plus 4x over x squared minus 5 over x squared. And if you're already, simplifying this in your head, that's great. You may even be convinced already, like if this is making sense, you might already be convinced that, yeah, it's going to be 10 over 3. That's the horizontal asymptote. All right, now let's go ahead and simplify. So I'm canceling my x squareds. I'm going to cancel that with this x here, and nothing cancels for that last term. In this term, those cancel. 1x cancels with one of those x's, and nothing cancels here. So if I write my limit, this becomes 10 plus 4 over x minus 5 over x squared all over 3 plus 2 over x plus 1 over x squared. Now, rather than kind of plug in infinity, which is really improper anyway, I'm just going to go ahead and take the limit by inspecting each term as x goes to infinity. So as x grows very, very large, what is happening to this term? Nothing's happening. There's no x involved. This one essentially goes to 0. This one also goes to 0. This one becomes 0, and this as well. So each one of those cancels out to 0 because when you divide by a very large number, the overall value gets very, very small. And what am I left with? 10 plus zeros is 10. 3 plus zeros is just 3. So that's the limit of this function as x approaches 0, or infinity. And again, if you change that to a negative infinity, you would just wind up with the same idea. Okay, the last situation is when the numerator has a higher degree than the denominator. Let's see what happens there. Okay, so before we jump into this one, I do want to show you on our computer again what that shape was. By the way, sorry, here's the last one. Remember, it has that beautiful dip in the middle, but then it does tend towards 10 over 3. The last one we're going to look at is this one. Very strange behavior, but notice that it's unbounded. The y values shoot off to infinity up, and it shoots down to infinity this way. So as x gets very large, the function is unbounded. It just goes like this. But why? So let's take a look at the limits. So the limit, as x approaches infinity, for x cubed plus 2x all over x squared minus 4. And I'm going to use that same technique of dividing by the highest power. The highest power in this situation is 3. So 1 over x cubed all over 1 over x cubed. And I'll multiply. Again, that essentially winds up being dividing. So this gives me the limit as x approaches infinity of x cubed over x cubed plus 2x over an x cubed all over x squared over x cubed minus 4 over x cubed. When I cancel, I'm left with the limit as x approaches infinity of that becomes 1. Here, this cancels, and I'm left with 2 x's. So that's 2 over x squared all over. It becomes 1 over x minus 4 over x cubed. All right, now it's time to think really specifically about our numbers here. So like I've been saying this whole time, infinity is just a very, very large number. As I shoot off to larger and larger numbers, what's happening? As the bottom gets large, this gets arbitrarily small, practically 0, not actually 0, but almost, right? Very small. Same here. This one becomes almost 0, basically 0, and this guy too. So what's happening here? The numerator I'm left with is like 1, but the denominator is 0. And is that possible? Can I divide by 0? Well, pause for a second, friends, because that's not actually the number 0. It's something incredibly very, very small. So what I have is basically the number 1, or something very close to 1, divided by something infinitely small. And when that happens, you get super big numbers, like super big numbers. I'm going to even do a few on my calculator really quickly. Let's do something really, really, really close to 1. So let's do like 0.9999999999999. Very close to 1. Now I'm going to divide that by something very close to 0. So 0.000001. Yeah, that's a super big number. It might be close to a Google. I'm not actually sure how to pronounce that number. But I'll try and make it larger there for you. And feel free to start playing with these things on your calculator too. Pick a number that's super close to 1, divide by a number super close to 0, and you're going to find you get really big numbers back, basically like as you're shooting off to infinity. So there's your calculus approach to understanding horizontal asymptotes. And if you continue thinking in terms of dividing by the highest power, once you start doing that in your head a little bit, you'll never have to remember all of those little rules that we went over in the beginning. Oh, if the degree is higher or lower, less than, equal, whatever. You don't have to remember that stuff because you can just quickly take a limit in your head and then remind yourself, oh yeah, when the degrees are equal, I use coefficients, or if the top is bigger than the bottom, it shoots to infinity and things like that. So I hope this has been kind of fun and enlightening and that you can take it into your own practice.